Namaste. In this session, we will study word embeddings. We will train these embeddings from scratch and use them for training the model. We can also visualize these embeddings with embedding projector. This is an example of an embedding projector where we are able to visualize the embeddings where we can see different words embedded in the embedding space. As we discussed earlier, we cannot use text content as it is and we need to convert the text into numbers. There are different schemes that are available for converting text into numbers. So, one of the scheme is one hot encoding, where what we do is we take the sentences and extract vocabulary from these sentences by tokenizing them and selecting unique tokens. For example, for the sentence the cat sat on the mat, the vocabulary or unique words are cat, mat, on, sat and the. Notice that the is included only once in the vocabulary list, though it is repeated in the sentence. To represent each word, what we do is we create a 0 vector of length equal to the vocabulary. So, here in our vocabulary there are 5 words. So, we create 0 vectors for each of the tokens and then we place 1 in the index that corresponds to words. So, for example, the we have a 0 vector for the and then we convert the 0 corresponding to the word the and replace that with 1. You can see the same thing for cat. So, for the word cat we have the position corresponding to cat as 1 and rest of the other positions are 0. Same thing with sat. To create a vector that contains encoding of a sentence, what we do is we concatenate these one hot vectors for each word. But this is terribly inefficient because a large percentage of positions will have 0. Imagine a 10,000 word vocabulary and if you use one hot encoding for each word, a very large percentage of positions will be 0. The second approach of converting these words into numbers can be achieved through encoding of word with a unique number. So, what we do is as soon as we get the vocabulary, we map each word to a unique integer. So, for example, for the word the cat sat on the mat, we can have a representation which is some numbers. So, here for word the we have mapped it to number 5. So, we see 5 at positions corresponding to the. So, there is the 2 times. So, there you can see number 5 appearing 2 times. Cat is assigned number 1. So, we see number 1 over here, then sat 4, on as 3 and mat as 2. So, this is an efficient approach where we have a dense tensor rather than a sparse tensor as we experience that in one hot encoding. However, there are 2 downsides to this approach. The integer encoding is arbitrary, it does not capture any relationship between words. An integer encoding can be challenging for a model to interpret, that is the second drawback. A linear classifier, for example, learns a single weight for each feature. Because there is no relationship between similarity of any two words and the similarity of their encoding, the feature weight combination is not meaningful. So, in order to overcome the limitations of first two approaches, we have an approach of word embedding. Embedding gives us an efficient and dense representation where similar words have similar encodings. Importantly, we do not have to specify the encoding by hand, and these encodings can be learnt during the training process. What is embedding really? What does embedding really mean? An embedding is a dense vector of floating point values. The length of a vector is a parameter that we specify. Instead of specifying the embedding manually, these are trainable parameters which are learned through the training process. It is common to see word embeddings that are 8 dimensional for small data sets and up to 1024 dimensions when we are working with really large data sets. A higher dimensional embedding captures more fine grained relationship between words, but they take more time to learn. Let us look at some of the embeddings. These are 4 dimensional embeddings for our example of the cat sat on the mat. So, here the word cat is embedded in 4 dimension, where you can see that each of the dimension has a real number. So, this is a dense representation and is quite efficient. We can also think of an embedding as a lookup table. After the weights are learnt, we can encode each word by looking up the dense vector corresponding to it from the embedding table. So, Keras has embedding layer that makes it easy for us to use word embedding. Let us see how to construct these word embeddings in tf.keras. So, here we use an embedding layer which is specified by layers.embeddings, where we pass the number of possible words in the vocabulary, which is total number of words plus 1 for padding, and we also specify the embedding of, and we also specify the dimensionality of the embedding, which is 32 in this example. So, with this we can define an embedding layer. The embedding layer can be understood as a lookup table that maps from integer indices, which stand for specific word, to dense vectors. The dimensionality of embedding is a parameter we experiment with. This is same as any other hyperparameters that we set or tune in the neural network. As an example, the number of units in each dense layer. When we create an embedding layer, the weights of the embeddings are randomly initialized, just like any other layer. During training, they are gradually adjusted via backpropagation. Once trained, the learned word embeddings will roughly encode similarity between words. As input, the embedding layer takes 2D tensors of shape, sample, sequence length, where each entry is a sequence of integer. It can embed sequences of variable length. All sequences in a batch must have the same length. So, sequences that are shorter than the others are padded with 0, and the sequences that are longer are truncated. Here we have 2 batches of the shape 32, 10, where we have batch of 32 sequences each of length 10. If we specify, if we have a batch of shape 64, 15, we have a batch of 64 sequences each with length 15. As output, embedding layer returns a 3D floating point tensor of shape samples by sequence length by embedding dimensionality. The embedding layer tensor, such a 3D tensor can be processed by an RNN layer, or it can be flattened or pulled and processed by a dense layer. Let us learn embeddings from scratch. So, here you will train a sentiment classifier on IMDb reviews. In the process, we learn the embeddings from scratch. So, let us define a vocabulary of size 10,000, and we have IMDb dataset from keras.datasets. IMDb datasets have movie reviews, and we will train our embeddings from the movie reviews. So, we use a load data function on IMDb to get training and test data along with their labels. So, when we import this data, this is already integer coded, where each integer represent a specific word in the dictionary. You can see that the first training example is represented with a list of integers, where each integer corresponds to a specific word in the dictionary. We can write a small decoder function to convert each integer back into the text. So, after applying the decoder function here, we get the words corresponding to the first review. We define 4 special tokens, which is pad, start, unknown and unused. The start token is inserted at the start of every review. So, movie reviews can be of different lengths, and hence we use pad underscore sequence function to standardize the length of the reviews. So, we pad each of the sequence with a special token for pad, and we do padding at the end, and we specify the maximum length for each of the sequence. So, if the sequence has lesser length than the max length, we add those many pads. If the review is more than the max length, we truncate the review. So, we apply the pad sequence function on both training and test data. Let us look at the first example again. So, you can see that the first example was less than 500 in length. So, we have padded that with number 0, which is the number corresponding to the pad token. Now, what we will do is we have the integer representation for every sequence, and each sequence also has the same length. So, let us define a model for classifying movie reviews, and in the process we will learn the embeddings. So, here we have embedding layer as the first layer that takes the vocabulary size, the embedding dimensions and the input length which is 500 in this particular case. Next, we use global average pooling 1D that returns a fixed length output vector for each example by averaging over the sequence dimension. This allows the model to handle input of variable length in the simplest way possible. The fixed length vector is piped through a dense layer with 16 hidden units, and we use ReLU as an activation over here. Finally, we have a last layer which is a dense layer with a single output unit with sigmoid activation function. With sigmoid activation function, it returns a float value between 0 and 1, representing a probability that the review is positive. Let us look at the model summary. So, let us draw this particular model in the note. So, we have a model. The first layer is an embedding layer, followed by global average pooling 1D. The output of that is piped to a dense layer, and we have another dense layer which is an output layer. This returns number between 0 and 1, and the input to the embedding layer is integer encoded strings. Each string is of the same length. So, we see that the input shape is 500 and we have defined embedding dimensions to be 16. We have defined embedding dimensions to be 16. So, what happens is we get a 500 length sequence, and for each of the 500 words we are going to return a 16th length embedding, and we do it for multiple such kind of sequences. So, this is really a batch dimension. So, here what happens is for each word, so let us say this is a sentence and sentence has multiple words. So, let us say sentence has 100 words. For each word we get embedding in 16 dimensions, let us say E1 to E16, and we get real numbers. So, as an example, let us say we get such kind of numbers. For all of them. In global average 1D pooling, what we do is we essentially average each embedding, we average across each of the embedding. So, we take average of E1, average of E2 and so on, average of E16. correct. So, average pooling returns for every sentence we essentially get 16 numbers. So, we have average pooling returning 16 numbers. So, that is the output shape for average pooling. Then we have a dense layer with 16 units. So, this 16, so this is the pictorial representation of that. So, we have these are input where there are 500 integers representing each sentence or each input in the text that we convert into an embedding so we essentially get the output of embedding is sent to global pooling. So, global pooling gives 16 numbers and these 16 numbers are fed into a hidden layer with 16 units. Then we have an output layer with a single unit which gives us the probability of review being positive. So, you can see that in embedding we have the vocabulary size is 10,000 and we need to get embedding in 16 dimensional space. So, we have in all 16 cross 10,000 which is 160,000 parameters to learn in the embedding layer. Global average pooling does not have any parameters. So, here number of parameters to learn is 0. Now, here you can see that there are each of the hidden unit has 16 inputs. So, there is a weight corresponding to each of the inputs. So, there are 16 parameters per unit and there is a bias parameter. So, there are 16 parameters and there are 16 units plus 16 bias parameters, that makes it to 272 parameters. You can similarly work out number of parameters for the output layer. Output layer has 16 incoming connections. So, there is a weight for each of the connection. So, there are 16 units, there are 16 weights per unit, there is a single unit and then there is a single bias term. So, we have in all 17 parameters. So, total number of parameters are 17 plus 272 plus 160k. So, it is 160 K 289 parameters is what you see over here. So, let us specify the optimizer, the loss function and the metrics to track in the model compilation phase and fit the model with the training data and training labels. Let us train the model for 30 epochs with batch size of 512. We also use the validation data here to obtain the accuracy numbers for the validation data along with the training data, and we capture the progress of training in the history object. Let us train the model. So, you can see that for the initial epoch we have loss of 0.69 for the training and loss of 0.69 for the validation. As the training progresses, the loss is coming down and the accuracy is going up. At the end of 30th epoch, we achieved accuracy of 95% on the training data and about 88.5% on the validation data. So, you can see that the validation loss decrease and then it is also showing some signs of again increase in the loss. So, which is pointing to the possibility of overfitting. Let us plot the information that we have captured in the history object and see how the training progressed. So, you can see that the training loss continues to go down as we train for longer, but the validation loss has plateaued after about 15 epochs. Let us retrieve the learnt embeddings for the words. Note that we have trained the word embeddings during the training, right. So, we will have the embeddings which shape the vocabulary size comma the embedding dimensions. So, our vocabulary size was 10,000 and embedding dimensions were 16. So, we get a tensor with shape 10,000 by 16. We can write these weights to the disk and visualize them with embedding projector. Let us go to embedding projector and upload both these files. So, by executing this particular code, we have written the weights to the disk. To use embedding projector, we need two files, one containing embedding and then the second containing the word. So, the meta file contains the words and vex file contains the embeddings. We download both the files on the disk and we will go to embedding projector and load the data. So, as an exercise, what you should do is you should upload both these files in embedding projector and visualize the embeddings. When you upload these two files, you see embeddings like this, and when you try searching for beautiful, you will see neighbors like wonderful.